Okay, so hopefully you caught the key phrase that he said. Everything that you know about history is false. He's going to tell you the real interpretation of history. I remember when this show first emerged on History 2, and the promo you were watching was for New Zealand, Australia, and it has way different music and tone of voice. He in the US promoted this show much more like sort of he seemed more breathless, I think is the word I'm looking for, as he's describing, the history you've heard is false, and I'm going to tell you the truth. There are hidden pyramids here. There's this, there's that, all these things that he's so certain of. He's going to provide us with the evidence of his interpretation, and we're supposed to throw out everything that we've known up till this point. I watched the whole series, and what I was really interested in was finding out what the red dot, he has red dots in the different states that he's going to go to and stuff. And there was a red dot in Oregon, and I was like, I wonder what that's going to be. So I watched every episode of this pseudoscientific show, and he never went to Oregon. So I'm not sure what he's claiming was there, but he never got there. But the idea is, it doesn't matter what other historians have said. One of my favorite episodes is when he says that there's evidence of the Mayan people in Georgia, and he says there's a pyramid buried there, but the government won't let him on the property to excavate the pyramid, and so he has to go other routes. And so he looks for evidence of Mayan blue dirt in Georgia, and he looks for linguistic similarities, like, for example, the people are Mayan, and then there are places that sound like they start with Maya in the region, like Miami and stuff. He's like, oh, see, the Mayans were here. So archaeologists say you're misinterpreting the data, and here's what we have, and here's our theory to account for what really is here. And he says, I don't have to explain any of that. That's too pedestrian for me. Let me just tell you my interpretation of the parts I feel like looking at. And that's really good evidence of a pseudoscientific approach. All right, here's another fun one. They'll declare just a whole new reality. Kind of this overlaps with the previous guy, right? He's going to discount all the previous data and tell you the truth, right? How about this new reality claim with this issue of something called polar body twinning? I had a student a number of years ago in one of my developmental psych classes, and we were talking about twins in class. And so she said, I'm a nanny, and the kids that I nanny are half identical twins. And this was the first I'd ever heard of such a phrase. So I was like, what do you mean by that? And she said they're identical on the mom's side and fraternal on the dad's. I'm like, what? So I said, I'm going to have to check out what you're talking about. So this is the result of me checking out what my student was talking about. And what she was talking about is this half identical twins. I got the Washington State Twin Registry here. What I want you to notice first off is just the first phrase in every paragraph. So we go polar body twin. Well, first off, the bigger cell. Okay. The polar body usually degenerates and dies. It says in this first paragraph. Polar body twins are theoretically caused when, in theory, polar body twins would share. However, there is no proof. So the Washington State Twin Registry says there is no evidence for such a thing. And if you look it up in the genetics websites and stuff, because I really searched to try and figure out if there is such a thing, I did ask the student, what made the mom think this was true? Like, what evidence is she pointing to that she's got polar body twins instead of fraternal twins? And what she was pointing at is how much they look alike, even though they are known to be, they have to be fraternal twins because they had two separate placentas when they were born, she said. Well, I would like to point out that identical twins can have two separate placentas. So this mom clearly doesn't understand, does not understand twins very well. So she thinks that they have to be at least partly fraternal because they have two separate placentas, but they must be at least half identical because they look exactly the same. There are regular siblings who look practically identical, right? You don't have to be identical twins to have a lot of physical similarity. So altogether, this mom just was misinterpreting, her twins and projecting more stuff onto it, and must have found this on the internet or something and skipped over all the theoretically in theory and there is no proof, right? But this is classic pseudoscientific reasoning to say, we need to test all of these twins. If you have 75% of your genes in common, then you must be this new kind of polar body twin, which, by the way, I'd like to point out that while it's the case that fraternal twins and regular siblings share about 50% of their genes, they can share more than that. Genes are a just random distribution. Like, I don't want to get into a bunch of details. If you want to learn more about this, you can take human sexuality from me, but the basic underlying premise is you have on average 50% of your genes in common if you're a fraternal twin or a regular sibling. You have on average 100% of your genes in common if you're an identical twin. So misinterpreting things does not make a new reality. It just makes an incorrect interpretation. Okay. So something that we've talked about, from my count, this is at least our third time, maybe our fourth already. I'm talking about Occam's razor, right? We always want to go with the simplest explanation of a phenomenon. And that's one of the places where pseudoscientists oftentimes fail. They'll have these really complicated explanations. Let me go back to this picture for a second. And let's talk about that America Unearthed show. One of the episodes was he went to Hawaii, where these two hikers say that they found a green obsidian. Obsidian is that really shiny, it looks like glass that comes out of volcanoes, and it can be any color, but they happen to have found a green obsidian spearhead while hiking in a volcano in Hawaii. And so the first premise that we're provided with, and of course, as viewers of the TV show have no knowledge of whether this is true or false, is that they don't typically have green obsidian in Hawaii. I've subsequently, after watching the show, found out that, yeah, they do. But okay, let's accept his premise. They don't have green obsidian in Hawaii. So he now has, second thing I'd like to point out is that we don't get to look at the obsidian spearhead because the hikers gave it to the National Park Service, and the National Park Service doesn't want the host of our show to look at it. He's supposed to be a well-respected forensic geologist, but the government one time after another just will not ever let him look at things because he's him. So he can't look at the spearhead, but we have a drawing of the spearhead. And we don't know exactly where the spearhead was found, but we have the hikers telling us it was approximately here. Okay, so we're already off to a great start. And then but don't worry, our host is going to just go ahead and run with all this information and comes to the conclusion through a long circuitous hour of TV that the spearhead originated in Mexico and that there must have been Polynesian travelers that made it from either the South Seas to Mexico and then to Hawaii, or from Hawaii to Mexico and back, not sure. And of course, I'm calling it Mexico just because I know you know where that is, but of course it would have been just North America in general. Anyway, so that we have an entirely new reality. We're going to ignore all the previous data on how, humans have migrated and the presence of green obsidian and other kinds of things. And we're going to declare this whole new reality that actually the Polynesians made it to the mainland and other kinds of things, right? We're just going to go ahead and suspend all disbelief of all the things that we have known and any questionable data. We'll just go ahead and gloss over that so we can have this whole new reality. We want to go with the simplest explanation. The simplest explanation is that what we've known so far should be linked to what we know now. Connectivity. So the most frequent finding should be the most trustworthy finding. Like if lots of people are coming to the same conclusion using different kinds of research, probably that conclusion is more reliable than when one person comes in and says, you know what I think probably happened? The Polynesians probably made it to the mainland, came back with this green obsidian spearhead. It managed to lay here in this volcano all these years and these hikers found it. That's what happened. Yeah, that makes the most sense. Is one person by themselves saying something completely different. We need to discount them and look at the most frequent finding. We don't want to look at the one person who says I have an explanation for everything that I've encountered here. I have a whole new reality for you. Here we go. Now, implied in this connectivity idea is that no one researcher has special knowledge. That we can't say that Einstein should be trusted over new researchers who are finding something different. Or that, Michael Gazzaniga, the guy who does all the research on split brain patients who have had their corpus callosum cut, that if he says it must be true because he's him. Like, no one researcher has special knowledge. Science moves forward. The person who was the expert in the field someday will be a footnote in a history book, right? Like, that's how the world moves forward, right? So no one researcher has special knowledge. We want to make sure that we're looking for the most common finding and putting sort of an more emphasis on this overall pattern than on this one trustworthy, we think that this is the person who knows more. Oh, that was an interesting hop. I wanted to throw one more comment in, and that has to do with how we decide whose data we believe. There has been a proliferation of debates on the internet over, the past, 10 years, when people started really using the internet a lot and stuff, and social media in particular, to share their ideas. And probably, starting in about 2015, it seems like people were really starting to get on the internet and say, here's my evidence, and so you guys probably should change your mind about something. And then somebody else will provide other evidence and say, I don't need to change my mind because look, this person that I found, they have evidence that supports what I already believe. One of the ways that you can approach that kind of debate scientifically is to say to yourself, because it's hopeless to say anything on the internet. I'm just saying right now, it's hopeless. But the thing is, if we look through confirmation bias for evidence to support what we believe, we can find something that will support what we believe. We absolutely can. I mean, we aren't believing things out of nowhere. We're believing things because it's at least explaining part of human experience or whatever. So what I've started noticing is people are trying to one up who their expert is. Well, I'm quoting this person who has these credentials and has had this experience, and therefore yours is de facto not as good because I've got this great person who I'm quoting. One person doesn't have special knowledge. And so what we want to look for is the overall pattern. And while it's true that the exception proves the rule, right, that we can find evidence that supports any perspective probably, we want to look for the patterns that are the most consistent, right, that are most in line with what other data has shown. Not what other stereotypes or expectations would say, but really what data has shown. All right. So here's my little diagram of what I mean by converging evidence. So overall, on the left-hand side there, you see different samples. One big key thing about converging evidence is even if you are using the same method, having a different sample of people in particular, right? If we're studying people, getting different kinds of people in your study can really boost the idea that we have the same basic outcome for different kinds of people, that it's generalizable. So different samples is a really important aspect of the converging evidence. So doing a complete replication like we talked about in chapter 1, doing everything exactly the same way, but our change is that we're actually getting a different kind of sample. So maybe the previous sample had used college students, and so now we're using middle-aged people, or previous research had used men, and so now we're doing women, or whatever the change is in that sample. Just by broadening out to different samples, we can really start to find out whether this is generalizable across people. And then across the top there, or what is the right side of the arrow, I've got like different styles of research that you could do: observational studies, correlational studies, experimental methods. The more different kinds of studies that are conducted that are producing the same basic outcome, the more confident we can be that this outcome is stable, reliable, probably valid, things like that. So, the more studies and the more varied the studies, the better. Getting weird premonitional flashes here. So converging evidence for global warming. So let's talk about this concept and talk about it through the lens of converging evidence. Okay, so here's one graphic that's showing CO2 levels over time. And so what you see is that it's been going up and it's been going down and going up and going down across millennia. But that since 1950, it's been going up, and it's been going up more than we've detected from the past. We can say at least that. Sea level rise, the objective measure of, losing land to the ocean, right? So sea level rise might be might be one study. One group of researchers might be looking around the world for evidence of sea level rise. Maybe another group is focusing on the temperature rise, the global temperature rise. So you wouldn't want to say whether it's getting hotter in a particular location, but average global temperatures. Warming oceans. Are we seeing higher temperatures in the world's oceans? And then finally, we've got shrinking ice sheets, melting glaciers, things like that. The fact that, these varied things, and I didn't even get into some of the other things that people have been looking at, like, for example, tree ring, cutting, looking at trees and looking to see whether they've had wet seasons and dry seasons and what things have been historically. Part of why this research is tricky is because the most informative trees would be those that are like the sequoias that are 2,000 years old and stuff. And so the argument is we shouldn't be cutting them down just to find out what their tree rings look like. So it's kind of tricky. They only have, small sample sizes of trees that have been previously harvested, and they've gone back and looked at the stumps, or they've had trees that have blown down, things like that. But so there are lots of different things that they've been looking at. And, most of the research, there are a couple exceptions, but most of the research is pointing towards the same basic conclusion, right? Various sorts of data all pointing to the same basic conclusion. Now, I'd like to point something out about this, though. The ones that I pulled and put into my little graphic here are all kind of getting at the same issue, which is temperature, right? Because ice melts when the temperature rises. That, if the ice is melting, then of course the seas are going to rise. So that's kind of two sides of the same thing. The ocean warming helps to melt the glaciers, and right. So one could argue, well, are these methods that different, right? Aren't they all really fundamentally tracking temperature? But when the premise that you're measuring is temperature rise, it kind of makes sense that everything that you're looking at has to do with temperature rise. My tree ring evidence, now that one's kind of a digression, isn't it? If we're going to be measuring the changes in the tree rings across time to give us insight into, rising or lowering temperatures in the past. It's a little bit different. But the basic issue here is that we have lots of different pieces of evidence that seem to be pointing in the same basic direction. But what we would want to argue here is that we've got converging evidence. Not that the science is settled, right? We've discussed this already. We don't want to say phrases like that shut off inquiry, right? We don't want to say, okay, we've all decided, stop looking at that. We always want science to move forward the way science should be moving forward, which is attempting to falsify this claim. So if we have converging evidence that has developed into this overarching paradigm that the global temperatures are rising, now that has become, that should, for scientists, that should become the target for falsifiability tests. So now temperatures are rising should be the status quo, and we should be looking for evidence that they aren't rising, right? That's how science is done. We should be attempting to falsify that claim. This is where it gets a little problematic in global warming circles, because if a person attempts to falsify the claim that the temperatures are rising, they become a climate denier. And when we call people heretical names like that, we're starting to move into the field of pseudoscience, right? So we want to make sure that we aren't experiencing junk science where everybody's finding what they're expecting to find rather than what's really there. We want to see falsification tests, things like that, and that way we stay in the field of science. All right. So with the principle of converging evidence, the goal is to eliminate rival theories, right? So when I'm Chomsky and I'm trying to figure out how language is acquired, my goal is to refute Skinner's theory. I'm not trying to find evidence that I'm right. I'm trying to find evidence that his interpretation is wrong. Right? So we want to eliminate rival theories is our goal. And our strategy is going to be to incorporate different research methods. Now, I'm not going to say that each researcher has to do different research methods. I'm saying that the field needs to be doing a variety of different research methods so that we can get the errors from one research method filling in for the errors in the other research method. So if, observational research is problematic because the observer maybe doesn't see all the information and record keeping is difficult, well, then a nice controlled experiment might fill in that gap by making sure that you don't have to be watching every single detail because you controlled every detail, right? We want to make sure that we have lots of different research methods so that, of course, there are going to be errors, but the gaps get filled by the different methods. The biggest problem with this principle of converging evidence is that it really does take a long time to generate sufficient studies to accomplish the task, right? To really answer the question. And this is really a frustrating aspect of science. As I'm talking right now, it's the end of April 2020. And so the big scientific question right now is every question is swirling around COVID. And, lots of details about it. Like, do antibodies that you might develop if you're exposed, do they protect you in the future? Right? Now there are lots of different ways to study that question. And unfortunately, it takes time for those kinds of studies to manifest themselves and give us the pattern. To really know the answers to some of these questions will probably take us years to really know. For example, if you have antibodies, you have to be exposed to it again to find out whether those antibodies work again. If you have antibodies right now and they worked right now, are you permanently protected? Well, by definition, we will only know that after time has elapsed. So science takes a while. It really does. It takes a while to get through these things and to really know. I'm thinking about back in the 40s, there was a very unethical study of men who had been identified as having syphilis. And I won't go into all the ethical details right now on that, but I just want to point out that in the 40s, they started the study on men who were identified as having syphilis. When antibiotics came on the scene, 8 years later, and could have at least halted the effects of syphilis and cured them from this point forward. They may still have residual effects from having been infected, but it won't progress anymore, right? Because we can get rid of that spirochete from their body. The researchers didn't offer it to the patients because they wanted to continue to study what happens as the disease progresses. And of course, it's a horrible design. The biggest problem with it is that they didn't get informed consent from the participants. They didn't know that they had syphilis. And so it's horrible. But part of the reason why scientists follow the progression of a known disease, you might be like, how do you need to know this anymore? I mean, how many people in the world have had syphilis by now, right? By the 1940s. But part of the reason why scientists do that is because they need to have sort of all the known data about people's lifestyles, whether they smoke or not, other kinds of things, and then follow it over time to see whether this manifests itself differently in different kinds of people. So it's time consuming. Sometimes it's not even doable to do this kind of research because of the ethics and things. And so a lot of times we think we know stuff especially in medical science, that we really just don't know because it takes a long time. We haven't got the data back yet, or we're not allowed to do that kind of research. So yeah, those are the big difficulties. Takes a lot of time. Might not even be able to do it. Now, conceptually, not pragmatically, but conceptually, the biggest risk, even, we've let it play out over many years, that we got all the data back, all sorts of, it's like, yay, I think we know the answer to our questions. It's possible that there was some kind of systematic error present in all the studies that contributed to our final product. And so those studies are all maybe consistently providing a particular outcome, and it's faulty across all of them because they all had that same error built into them. It might be a bias. It might be maybe a measuring error. It might be they all use the same kind of sample, and because they wanted to try and be as consistent as they could be as they were going through, observational methods, correlational methods, experimental methods. So they said, well, let's try and use the same kinds of participants. So at least we're holding that steady. And it turns out that kind of participant was like an anomaly, and anybody else wouldn't have reacted the same way. The biggest risk is something systematic, giving us an overall incorrect picture. That's the biggest risk. So the good news is it's pretty unlikely that if you have enough studies from enough different labs using enough different methodologies, that you would actually have some kind of systematic error. So our biggest risk is also probably the least likely risk. Now, if you have one researcher doing all the different methods, it makes it more likely that you'd have a systematic error, right? It's much better when you have lots of different people all exploring the same question from different angles. That really helps to protect us from systematic errors. All right, so scientific consensus emerges brick by brick. Most science isn't a breakthrough, it's incremental, brick by brick, right? There is no great man theory where you fall asleep in front of the fire and aha, you have the solution to the problem. That's just not how it works. It's little bricks, all of us contributing our little part to help us to understand. I have a example that I just went through. I shouldn't say just. I've been working on this project for about 20 years, and I finally got it published last summer. And I keep running up against a brick wall, so to speak, with this project because I was studying an aspect of memory that everybody takes for granted, but there's actually no data to support. Back in 1972, a model was developed to explain how if you process information deeply, it'll be more memorable than if you process it shallowly. So a lot of people started researching what is deep and what is shallow and other questions like that, and they were always using immediate tests of memory, either a 30-second delay or less. I mean, in the modern research, the memory test is like not even a second after introduction of the word. I'm like, wait, what kind of memory is that? Anyway, so they've been studying it like immediate memory, however you want to define immediate. And I'm not seeing any evidence in the research, and I've been reading on this since 1995, no evidence in the literature that anybody has ever collected data to find out whether over the long term, and by long term I mean something more than a day at least, that people are retaining material differently if they processed it deeply or if they processed it shallowly. So I got a group of students together and we collected data on 3 different versions of the experiment. And in one version, the participants retained it for 1 week. In the other 2 versions, they retained it for a month. So we got it all packaged up, sent it off to the journal Memory. And the editor said, well, this is a really well done study. It's really well written, but I just don't think my readers will be interested in it. So I sent it off to the Journal of Memory and Cognition, and I got exactly the same feedback. I don't think our readers would be interested in this. I sent it off to the Journal of Learning, Memory, and Cognition, and the editor said, this is a really, really well understood phenomenon. And that one I finally decided to push back, and I said, understood how? Because I can't find a single journal article that was published on this topic. And the editor said, well, I did a quick Google search and you're right, but I don't think my readers would be interested in this. So I finally found another Journal of Cognitive Psychology, and I sent it off. And this time I included in the paper, there are no studies on this. We're all taking it for granted, but nobody has ever actually quantitatively established that deeper processes lead to better memory over any amount of time. And finally got it published. Yay. it was like the field of memory research, particularly pertaining to learning the levels of processing model, had forgot about this step-by-step, incremental, brick-by-brick, we need to fill in the details before we leap ahead and assume stuff about how memory works, right? Most science is brick by brick. Just because everybody agrees doesn't mean they're right. It was possible that I could have administered the shallow versus deep tasks, come back a week later or come back a month later, and the two groups scored exactly the same, or that the shallow group actually ended up scoring better. It's possible. We didn't know it because nobody had ever done any data on it. Just because everybody agrees doesn't mean that they're right. Turned out that they were, but I mean, it doesn't mean that they are. We need data to establish that. And in fact, somebody else should replicate my study. What if I did something wrong? The politics of publication can also produce the appearance of consensus. It's my story about the editor saying my readers won't be interested in this. That's a good example of what we call politics of publication. The editor wants their journal to be read, obviously. So they want to publish papers that seem like they're groundbreaking, like they are, introducing something surprising. If you can tie it to some subject that's sort of a hot topic right now, they like that. So I'm not talking about politics of necessarily it being like a famous person. That's a separate part of politics. I'm talking about like the subject. They want their journal to be read, and so they want to make sure that they're publishing things that they think will attract readers' attention. And so if only those things that are currently considered interesting and hot are published, you can imagine that there are probably some things that are languishing that might be contrary to what is currently popular or currently in vogue, right? So only publishing things by famous people or only publishing things that they think their readers want to read can lead to the appearance of consensus when in fact there might be something disparate out there. When we have fresh eyes and new data, it can always throw a theory into question. So one of the nice things about science is that there's always new scientists coming on board, right? There's always people graduating from grad school, entering into the world, and they've got their own viewpoint on things. They're looking at things from another angle, or maybe they are familiar with a technological approach that would allow them to explore something that previously was a mystery and now is something that's actually something that can be studied. So as science moves forward, we're always going to have people attempting to falsify the existing theory, and they may actually start to undermine the theory, right? And that's the beauty. If the theory stands up, terrific. It may be right. It may, in fact, be one step away from being proven, right? It might be true. It might be the correct interpretation. But if all these new people are coming on board and they're collecting data in their own way and things, we may find out that the theory is actually faulty. Now, I wanted to leave you with this optimistic interpretation that, when we have well-designed studies, which is why we try and train psychology students to be scientists first, so that you'll know how to design good studies or how to recognize them when you see them. And then nonpartisan publication practices. And what I mean by that, again, with nonpartisan, it's like, I'm not just favoring you because you're famous, or I'm not favoring this topic because it's something I find interesting. If you have a combination of well-designed studies and the nonpartisan publication practices, we should be able to produce trustworthy conclusions. Now, I just pulled this one really quickly off the internet because it has the word converging evidence in its title. And of course, it also has, sex in the title, which is always sexy. So that's always a good one. But I pulled this out because converging evidence, and then they threw in ubiquitous. Ubiquitous means really common or frequently seen. So here they are reporting exactly what I'm talking about. The idea that, lots of different researchers are coming to the same basic conclusions. If you're interested in what this is about, I put the citation at the bottom so you could find it because it's kind of an intriguing thing, but it's not the point of this class. But, well-designed studies and then publication practices that get good data in front of readers' eyes, regardless of whether it's something that the editor is passionate about or, it's a famous person or not. That's what we're hoping for, is that we can make good, trustworthy conclusions in the long run. So, all right, That's good enough for this chapter. I will see you guys back in the next chapter.